In this session, I would like to talk about pipelining. So using the pipelining, we are going to achieve parallelism. That means we are going to execute multiple instructions at a time. How it is possible, we will see. But we will be having only one set of hardware. So that is what the magic of pipelining. To understand that, better you understand this analogy. Example, let's say you have one employee, let's call him Raju. So you are going to have some hotel and he is an employee now. So Raju is going to make rotis. He is a roti specialist. Then when you observe Raju's functionality, what he is going to do to make a roti is, first of all, from the dough, he is having a very big dough, let's say like this. Now, from the dough, he is taking some portion and he is making a ball first. Okay. So this is the first step, making a ball. Then he will take that ball and he is pressing it. So by pressing it, he is making a round roti like this. Okay. Now it has to be finally fried. Okay. So here he is pressing it. Let us say it is press stage. After that, he is frying it. That's the third step. So in the third step, he might require stove or everything. So but he doesn't require stove in the press stage and making ball stage. So finally here he will be making the fried roti. Okay. So that is about the process. Now assume that each stage takes 5 minutes of time. Then if someone orders a roti, then he will take 15 minutes to serve. Okay. If you ask two rotis, what he is going to do is, again he will repeat this process. This is for the first roti. If you ask second roti, he is going to take a ball again. That means he is going to make a ball again from the dough. Then he will be pressing the ball and he is making a roti and he is frying it. So again three steps. So it takes 15 minutes. Then if there are 10 rotis to be prepared, then how much time he will take, 15 minutes into 10 rotis, it will be 150 minutes. So that is about his inefficiency. Now the same Raju, that means the Raju's functionality is nothing but three parts, right? We'll divide the Raju into three parts with respect to functionality wise. Assume that we can cut Raju into three parts. Okay, it's possible. So that the first cut, we will be dividing Raju into three pieces. Raju 1, Raju 2, Raju 3. So this Raju 1 knows only how to make balls. Okay. Now this Raju 2 knows only how to press the balls, and this Raju 3 knows only how to fry the roti. Okay. Now in that way we divide. So that you are going to get the advantage, we will see that. To understand that, let us take three Rajus now. Raju 1, Raju 2, Raju 3. Now Raju 3. In the first 0 to 5 minutes, what is going to happen is, this Raju 1 is going to make a ball. Okay. So ball number 1. So at that time Raju 2 and Raju 3 cannot work, because Raju 2 requires the ball to get, start working, correct? So that's why after 5 minutes, if you see, that means in the duration of 5 to 10 minutes, what can happen is, so this ball can be taken by this second Raju. Assume that, let's say, there is no delay between, communication here to here. That means once ball is prepared, so it takes 0 time for Raju 1 to give it to Raju 2. Then in the duration of 5 to 10 minutes, Raju 2 will start working and he will press it. In the third duration, that means 10 to 15 minutes duration, so what is going to happen? So the roti will be prepared, correct? Now let us continue this process. Before continuing, I will ask one question. My dear Raju number 1, see, after 0 to 5 minutes, that means after 5 minutes, in this slot 5 to 10 minutes, you are free, right? Why are you free? Why don't you make one more ball? Yes, it is possible. Here also we ask, Raju, in the third step, that means in the duration of 10 to 15 minutes, you pick up some piece of dough again and make third ball. Now here, Raju 2, what he can do is, he can press. Then we'll ask, my dear Raju 2, why don't you press another ball? I don't have ball. Don't lie. You have a ball, right? See here, 2. So that's why second ball he can press. Now here, in the next step, if you see 15 to 20 minutes, then the Raju number 1 will pick the fourth ball, Raju number 2 will press the third ball, Raju number 3 will fry the second ball. In that way, so see the idea. 3 stages are working at a time, right? So that's why you get the benefit. But in the serial execution, either Raju was preparing the balls, otherwise Raju was pressing the ball, otherwise Raju was frying the ball, right? Frying the roti. But here at a time all the devices, otherwise all the functionalities are getting working, right? Now the 20 to 25th minute if you see, then 5 here, 5th ball will be prepared, 4th ball will be I can say pressed, and 3rd ball will be fried in that way. Next you can easily understand here 6, here 5, here 4. So in that way it will be continued. Now we'll try to understand this idea. So after 15 minutes what is going to happen is the first roti will be prepared. Sir, in the first serial model also after 15 minutes one roti got prepared. What is the difference? The difference comes when you execute multiple instructions. Otherwise, when you prepare multiple rotis here, when you prepare multiple rotis, see, the second roti is now prepared here, right? What is the time slot? 15 to 20. That means after 20 minutes, second roti got prepared. After 25 minutes, third roti got prepared. After 30 minutes, fourth roti got prepared. That is what the idea about pipelining, right? So now I can say that for every 5 minutes, one roti will be prepared here, but in the serial model for every 15 minutes one roti will be prepared. So there is a difference, isn't it? So there is a threefold performance improvement, understand? So to have that kind of threefold performance improvement, you should have 3 stages, right? If you had 4 stages, same problem, then probably you would have 4 fold performance improvement. So that is what the idea about pipelining. Now the same thing we apply for our instruction execution. So what we do is, we are going to, however, the instruction execution, if you see, this is your instruction execution. Let's say this is a circuit, and when you give instruction number 1 to this circuit, it is going to execute. Let's say it takes 15 minutes of time. Then what we can do is, rather than executing instruction 1 under this circuit, then again after that feeding instruction 2, then after that feeding instruction 3, if you do that, then every instruction will be executed after 15 minutes, right? But if you do the same thing, that means for that you divide the circuit into some stages and make sure that every stage works at the same time, then you can get the performance benefit. Okay, so we will see that is the idea about pipelining. The entire story about pipelining is nothing but how effectively we can give the work to all the stages, right? We will see that, but there are some problems also, we have to solve them. Okay, I will explain the problems also. Let us begin with pipelining of instructions. Now we'll go into the details of pipelining. Before going to that pipelining model, first of all we'll see serial execution, how we execute serially. Example, let's say you have hardware that is having these 5 stages: fetch, decode, ALU, memory and write back. In fetch, let me revise, already in control unit I taught that, right? In fetch we fetch the instruction and we increment the program counter, you know that, right? After that, that fetched instruction will be decoded by this decoding circuit. So that decoder is going to understand the instruction. Based on that, appropriate control signals will be generated, and we have studied how to generate the control signals in control unit, right? Please go through that. So finally control signals will be generated here and the appropriate instruction will be understood here. Then the appropriate registers will be read here. Everything will be done in decode stage. In the decode stage, so we understand the instruction and we generate the right control signals, and at the same time the instruction might contain some of the register addresses. We go there and we read the data, and after that ALU will be done. Then of course I taught you in control unit how real execution flow goes, right? So after that we do any arithmetic, if and all, if there is an arithmetic. Then later, so if you want to write something into memory, otherwise if you want to read something from the memory, then we do in the memory stage. Then after that the next stage is write back. If you want to write the result in the register, otherwise if you want to store the return address because of your instruction, then we do here, right? Typically in which instruction we do, we store the return address in the register file. We do that in function calls, right? Example, if you have an instruction called call R2, then what is going to happen? We will be storing the return address of the next instruction in some register file, right? Especially that register is called link register, that is implicit, doesn't matter at this moment. Finally, these are the 5 stages. So we can implement our hardware in 5 stages, you know that, right? So assume that let's say fetch takes 200 picoseconds, decode takes 100 picosecond and ALU takes 200, memory stage takes 200 picosecond and write back takes 100 picoseconds. Then how much time load instruction takes? Example, let's say you have these like individual time units for each stage. Then what is the typical time load might take? So load requires definitely fetching, right? We have to fetch that load instruction, then 200 units. Then we have to decode it, 100 units, 200 plus 100, 300. Then we have to do arithmetic because effective memory address we have to compute. Then we have to utilize arithmetic logic unit. Then later, do we need anything to load from the memory? Yes, load instruction itself says that we have to load from the memory. That's why there is a memory access 200. And after that, are you writing anything into register? Yes, in the register also we are writing. Let's recall. Load R1 100 of R2. Correct? Here you see in the write back step we will be writing the value which is located at 100 plus R2 into register R1. So register R1 is in the register file. To write that into register file R1, register R1, we have to use this write back stage. That means finally 200, 100, 200, 200, 100. So finally how much time it will take? Definitely 400, 500, 700, 800. So this load instruction typically at least it requires 800 picosecond, right? Now if it is store instruction, then probably store instruction requires fetching the instruction, decoding it. Then is there any arithmetic? Yes, sometimes your instruction might be like this: store register R1 value into 100 of R2. Then we have to find out the effective memory address where you are going to write the value of R1. So that's why, so definitely it is required here ALU also 200. Now after that memory, yes, in the memory we will be writing the content of R1. So that's why 200. But we are not writing back into the result into the register, that's why nothing. So definitely 200, 100, 300, 500, 700. You require 700 picoseconds if the instruction is store instruction. Similarly for add, it might require 200 here, decode 100. So ALU require 200. But any memory, are you writing anything in memory? No. Are you writing anything in the register? Yes. So that's why 200, 300, 500, 600. You require 600 picoseconds. Now branch instruction. Example, your branch is like this. Branch to a memory address something like R2. R2 contains one memory address, branch to that. Okay. So that means jump to that R2. Then for that, so probably we have to fetch that instruction, correct? Then you have to decode it 100. Then any arithmetic, you don't require arithmetic, right? So probably sometimes what happens, maybe your branch is relative. That means you want to branch to probably I mean like this, branch 100, where you want to you want to take the branch especially relative to program counter. That means program counter at this moment, let's say 200, you want to jump to 300. For that we write like this: whatever the program counter shows, with respect to program counter I want to move 100 units. Such kind of instructions you might write. Then probably ALU is required 200, but after that no memory, nothing to write. So nothing to write into register, that's why these two units we don't use. Then probably you require 500 picosecond, right? Doesn't matter, right? Try to understand, but if you don't understand also no problem. Now finally, if you have to design a hardware, then we have to remember one thing. In these four instructions, which one is lengthier? 800 picosecond. Then why I am teaching all these things? Because finally, let's say to execute any instruction properly without any mistakes, then your clock cycle should be, assume that let's say you want to design your circuit such a way that that entire instruction execution you want to perform in one clock cycle. Okay, that is what my assumption generally. So people design like that. If this entire circuit to do its entire work in one clock cycle, then what should be the length of the clock cycle? That should be definitely 800 picosecond, because sometimes maybe your instruction may be load that requires 800 duration. That's why we can fix the clock cycle to 800 picosecond. Remember it. Now let's come to pipelining. If it is pipelining, what we are going to do is we are going to divide the work into the circuit into 5 stages like this, right? 5 stages. So now each stage requires how much time? Sometimes 200, sometimes 100. Whenever you have uneven delays, then we have to go for maximum delay, because see, though it is very fast, but because of these 200 picosecond delays, these stages also will get delay. Okay, that's why the each stage, if you have uneven delays, then what we have to do is we have to take the maximum delay into the consideration. Okay, now we will see more details of that. Assume that, let's say, I will plan my stages such a way that every stage takes 200 picosecond. Okay, 200 picosecond. Though some stages might not require that much time, still we give, because the maximum stage delay is here 200 picosecond. Now we will see the advantage of pipelining in this model. Like if I use pipelining, what is going to happen, we will see. Now we'll see pipelining model. In pipelining model, first thing you learn that we divided our hardware circuit into 5 stages, right? So each stage we prepared such a way that example, there is some work right in the stage. So the work whatever we are doing in that stage is maximum 200 picosecond time, correct? So what we do is we fix our clock cycle to exactly 200 picosecond, and that clock cycle time is exactly equal to one stage time. But in serial execution, in non-pipelining model, we fixed our clock cycle to exactly equal to one instruction execution time, which is nothing but 800 picosecond, right? But here what we are doing is we will be taking one clock cycle as one stage time. Okay, and the stage duration is already fixed, right? So what is it? It is 200, right? It is maximum stage delay. So now what is going to happen is, just forget about this entire picture, just focus on the first row. What is going to happen is, so the first instruction will be, now you have a hardware, right? If you see the hardware, that hardware has 5 functionalities, right? 5 components. Otherwise, whatever the number of components, they can be designed such a way that they do instruction fetch, and they can do decoding, and they can do execution, and they do memory access, they do write back. Please go through that control unit topic where I explained the hardware, right? So we have seen the entire hardware unit. So all are independent. We such a way we planned them so that, so when you are fetching the instruction, then really decoding and that execution hardware and that memory write back, memory write, otherwise memory access stage, and the hardware related to write back, otherwise they don't have any work, right? In that way, independently we designed. What I want to tell you is, when you are doing instruction fetch, then this decoding circuit and execution unit like arithmetic and memory access. What is the meaning of doing memory access? There will be main memory, and we will be accessing the memory. How it is related to decoding, right? So that's why, so there is no relation between memory and these stages, they are independent. So there is no dependence in the circuitry, right? But only one question you might ask, sir, instruction fetch, in the instruction fetch we are going to fetch the instruction from memory, right? Which memory? Let us say main memory. And in memory access, what are you doing? We are also fetching the operands here, right? From where? Main memory. Sir, there is a clash, right? You have 2 stages. Really, if you want to do pipelining, then this stage and this stage should work parallelly, correct? At a time, simultaneously. But how simultaneously they work, sir? Because both requires main memory, and maybe example, let's say this is the memory bus, okay, through which we send the address, and there will be data bus through which we get the data. Okay, this is your main memory. Now instruction fetch stage and memory access stage require same main memory. How these two circuits can work simultaneously? They can't work, right? That's why, remember one thing, the architects are designed the machine such a way that there is a separate memory for instructions. Let us call it as instruction memory. Okay, so let us assume that we have 2 memory systems. One is instruction memory. How it is implemented doesn't matter. What is important for is, we have instruction memory and data memory separately. then only these two stages can work independently. Otherwise there will be dependency between these two stages, then it will be problem, right? Why it will be problem? If you want to understand, you should understand this entire flow of execution, how we are going to do the execution in pipelining. So far we did not discuss how pipelining works in our this model, right? In instruction execution we have seen in roti model, like how to prepare a roti with pipelining we have seen, but same thing of course here also, but we have not seen here explicitly. Let us do that. So at this moment you remember instruction and instruction fetch stage and memory access both requires memory. That's why what we do is we store instructions in separate memory and we store data in separate memory so that they can work independently. Remember it. Now with that situation you focus. So what I want to say finally is the instruction fetch hardware, decoding hardware and this execution hardware and memory access hardware and write back hardware all are separate. So instruction fetch does not require any hardware about write back. Okay, so there is no dependency, all are independent. That means at a time you can make all these things work. If that is the case, what is going to happen is, assume that let's say I am using one clock cycle, let's say time period. One clock cycle is now 200 picosecond. In the previous example we took like this, right? So in the first clock cycle, what we are going to do is we are fetching the first instruction, okay, instruction number 1. Then in the second clock cycle, that means in the second 200 picoseconds, then we will be decoding that instruction. That's it. In the third picosecond, we execute that instruction. In the fourth picosecond, we do memory access if and all if it is there. Then in the fifth clock cycle, we will be writing back the result. Okay. Now, what I want to tell you is, in the second clock cycle, that instruction fetch stage or circuit related to that is idle, right? When you are decoding the second instruction, so instruction still the fetching instruction, that components are idle. Why don't you plan your machine such a way that, so in the second clock cycle, your machine's instruction fetch stage should fetch the second instruction. That is what you have to plan. For that we have to design hardware such a way, okay? So that means, example, you have instruction fetch hardware, whatever it is, okay, there is a hardware. We know how that hardware is going to fetch the instruction. Then we have to ask that hardware to fetch instruction for every clock cycle. Yes, because it requires only 200 picoseconds. In the second 200 picosecond, it can do it, right? If you ask such a way, we can design, not a problem. Why to wait for entire duration, right? So that's why. So the second instruction is getting fetched here. At that time, so the first instruction is getting decoded, right? So decoder circuit and fetch, that's why instruction fetch circuit and decoder circuit should be independent. There should not be any dependency. Now in the third clock cycle, we will be executing the first instruction, we will be decoding the second instruction, we will be fetching the third instruction. In the fourth clock cycle, we will be accessing the memory for the instruction 1, we will be executing the second instruction, we will be doing decoding of third instruction, we will be executing fetching the instruction of fourth one. In that way, so we can do. Now I can continue like this. In the fifth clock cycle, write back of first instruction, memory access of second instruction and execution of third instruction and decode of fourth instruction and fetching the fifth instruction are possible simultaneously. Now after that, you see, in every clock cycle, 6th, 7th, 8th, 9th, if you have infinite instructions, then everywhere you can see that all the stages of your, see, this is the clock cycle. In this clock cycle, write back stage, memory stage, execute stage, decode stage, instruction fetch stage, all are occupied. So you get parallelism, right? Now we will see the time required to execute the first instruction, 200 picosecond. Already I told you. So pipelining doesn't add any effect in executing one instruction, right? But when you execute multiple instructions, you are going to get the better throughput, right? But for particular instruction, again it takes 200 picoseconds. Now in the second, not 200, it will be 200, 200, 200, 200, 205, right? So after 1000 picoseconds, we are going to get the first instruction execution. But then you see, the second instruction is immediately executed after 200 picosecond. Now after 1200 picoseconds, second instruction got executed. After 1400 picosecond, third instruction got executed. Assume that let's say you are executing 10 instructions. How much time it will take? We will see for 10 instructions. Just let's list out. I1, instruction 1 requires 1000. Instruction 2 requires 1000 plus, see here. After 1000, just after 200 picoseconds, second instruction also done. So 1200. I3, 1400. I4, 1600. Now we can have a formula here. What is that? I4 1600, I5 1800. Can I say like this? 1000 plus first time 0. Second one is 1000 plus 200. Third one is 1000 plus 2 into 200. I understood. So finally I5 is 1000 plus 2 into the 200 into how many? You just check it out. I should get 1800. Can I say that 9? So 1000 plus, so here 200 into how many? 4, right? So 1800 I5. So what is this 4? For this 5 minus 1. Then I10 equal to 1000 plus 200 into this 10 minus 1, 9. So it will be 2800 picoseconds. Now let us use that old model where we have designed a circuit so that that circuit is intermixed in such a way that so one instruction execution takes exactly that 800 picosecond, right? Here the first instruction is taking 1000 picosecond here, but here 800 picosecond. It looks like it is better, right? But to execute two instructions it requires 800 into 2, 1600 picosecond. To execute 10 instructions it will be 8000 picosecond. 8000 picosecond versus 2800 picosecond. Definitely it is better, right? Which one is better? This one, pipelined execution. Now we'll see the speed up formula. What should be the formula for speed up? If you want to know the speed up is nothing but, if you want to know the speed up for this problem or pipelining, because of pipelining how much performance improvement you got, that is nothing but speed up factor. Speed up factor equal to time required to execute. Example, let's assume that what is the speed up you get for 100 instructions? That is the question. You are executing 100 instructions. For that, how much speed up you are going to get? First of all, the formula, speed up formula is the time required in non-pipelining by time required to execute in the pipelined model. So that is the formula for speed up. Okay, now let me repeat. If you want to know the speed up of pipelining for some 100 instructions, then the formula is time required to execute that 100 instructions in non-pipelining mode by time required to execute them in pipeline mode. Let us solve. So time required to execute them in non-pipeline mode is nothing but, so example, so all the details are previous details, like so that non-pipelined is taking 800 picosecond for one instruction. Then 800 into how many instructions? 100 divided by time required for pipelined. So time required for pipeline for 100 instructions, we have a formula. What is that? In this one, I10 is nothing but 1000 plus 200 into 9. Then for 100 instructions, that means you should know when the 100th instruction is executed, because by that time everyone is executed. So what is the time required to execute 100th instruction? It will be 1000 plus this 200 into 100 minus 1, 99, correct? So I can say that 1000 plus 200 into 99. 1000 plus 200 into 99. Right? Let us simplify it. It would be, can I say 800 into 100 is 8 into 10 to the power of 4 by 1000 plus, what I do is I write like this, 1000 plus 99 2s are 198, 19800. It would become 80000 by 1980 and 1000. That means, so 19,800 plus 1000. Is it not 20,800? Yes. So if I simplify it, 00 will get cancelled, 00 will be cancelled. So it will be 800 by 208. If I approximate it, like if I take in the place of 80, it will be 200 by 800, which is nothing but 4, right? Otherwise you get something 3.9 or something you get, you have to calculate and check. Finally, the performance improvement, if you see, through speed up, the speed up is 4 times, fourfold. So why fourfold? Why not fivefold? You have 5 stages, right? But see, the problem was in the linear, I mean that sequential model, the time circuit took is 800, right? But here these 5 stages are taking, because we took maximum delay, right? For each stage, though some stages are taking less time, in this model what we did, because of pipelining, we took even delay, right? So in the pipelining, you remember, for better performance, all the stages should have same delay, okay? That's why we fixed it to maximum delay. So 200 into 5000. So there we are getting the difference. So here you are taking 1000 picoseconds for one instruction execution, but in sequential execution you are taking only 800. But of course, because of the parallelism, we got the better idea. So at least 4 times is definitely better than nothing, right? So that's why pipelining is going to give the performance improvement because of the parallel execution, right? Now remember one thing, almost it is like number of, so that the improvement is one fold or two fold or three fold. It's like, if you have 10 stages, probably you might get a 10 fold performance improvement, but it is not always true. So why don't you divide our stages into 10 or 20? Because if you have 5 stages, then you are getting almost 4, right? That means 4 times. If I have 100 stages, I might get 99 times improvement in the performance. Is it true? No, it is not true. Why? We will see. Okay, I will tell you the reason.